let's do it. So this is the yellow packet. Chapter 22 is organic. Now, I don't teach organic. Dr. Berman teaches organic. So like if you were to go into chemistry or biochemistry, organic chemistry is usually the next class that you would take after this. It's like its own branch of chemistry. Organic molecules behave and act a certain way and are actually named a certain way, which is what we're going to start looking at today. So we kind of keep organic in its own world because the properties between organic molecules and like ionic molecules are completely different. So just comparing like sodium chloride to butane. Butane is an organic molecule. Okay, these both have similar molar masses. So like sodium chloride is, it's gonna let me write, 58.5 grams per mole. And butane is 58.1 grams per mole. Okay, so they have a similar molar mass. However, they act and behave extremely differently. So their properties are going to be like way different. So we know this is, of course, ionic. And butane is what's not ionic? Covalent. Thank you so much. It is covalent. So all organic molecules are going to be covalent molecules. NaCl has a melting point of about 801 degrees Celsius. It's super high. It is really hard to melt salt. And its boiling point is 1413 degrees Celsius. Very, very hard to boil salt. Whereas organic compounds tend to have much lower melting and boiling points. The melting point of butane is actually negative 138 degrees Celsius. And the boiling point is actually 0 degrees Celsius. Okay, so way lower, which is typically true of covalent molecules anyway. Ionic things, do they dissolve in water? Yes, in water, because water is polar. Now, organic things tend to be non-polar, so they don't usually dissolve in water. So this one is not soluble in water. If you try to mix butane and water, they do not mix. This is very non-polar. If you see this, it's very symmetrical. Okay? Carbon and hydrogen actually have very similar electronegativities anyway. So it is a very non-polar molecule. And you can't like set salt on fire. This doesn't burn. Sodium does, but not sodium chloride. Whereas almost all, not all, but most organic compounds burn with oxygen or when they're in the air. Okay, so these guys over here, this is a kind of representation of most organic molecules. Organic really just is the study of molecules that are based on carbon. Okay, so organic is essentially study of carbon compounds. So why do you guys think carbon has like its own chemistry? Yes, Troy, what do you think? Because it makes 4 covalent bonds. That is one reason it's very special. It always makes 4 covalent bonds. Absolutely. Yes.
Carbon is the basis of life.
Yes, we are carbon-based life forms, right? Nothing else is made of anything different other than carbon. There's so much carbon that it really only makes sense to study it in its own field of study, you could say. So these molecules are going to be really important. They do a lot of things in our everyday life, and we are going to talk about the differences and all of the things associated. So this is just a snippet. If you want to take the full course, that would be the one you would take after this class. So organic compounds. Now, when I say molecular geometry, probably think back to 161 and you're like, I don't know what all the shapes are. I don't remember. Well, the only ones you need to remember for organic compounds are tetrahedral, trigonal planar, and linear. Okay, those are the only shapes that you are going to see. If you have 4 domains, like 4 things bonded to carbon, sorry, this is 4 things bonded, it's going to be tetrahedral. If it is 3 things bonded, 3 things bonded, it is going to be trigonal planar and have 120 degree angles. And if it's only got 2 things bonded to it, 2 things bonded, it is going to be linear. Okay, so those are really the only 3 that you're going to see with carbon. We're going to throw in some oxygen and some nitrogen in there, and they all kind of bond with carbon as well. But those are the only shapes you're going to see. So again, this is something from 161 you may or may not remember. Essentially, when you have 4 domains, the hybridization of that molecule is sp3. There's an S and 3 Ps that are involved in the hybridization. If there's 3 things bonded to it, it's sp2 hybridized, meaning 1 S and 2 P orbitals are used. And if it's 2 things, it's sp hybridized. And if you don't remember what those mean, honestly, if you just memorize tetrahedral and sp3 is when you have 4 things on there, that's fine. That works. Okay. So there will be some questions about this on the homework, so kind of keep that in mind. So these are the only 3 hybridization and geometries. Only 3 hybridizations / geometries in organic compounds. Main reason being, carbon only makes 4 bonds. So we really can't do anything else. And it really doesn't like to have lone pairs. So none of these molecules have lone pairs on it. It's always 4 bonds. Could be a double bond or a triple bond, but it's going to be 4 total. Okay, so that's the whole reason. Carbon makes 4 bonds. So it's either 4 single bonds, it could be 2 singles and a double, or a single and a triple, but that's like all you're going to see for carbon. Okay, that's really important to remember. 4 bonds. Okay, so we are going to start looking at these different molecules and how they behave, and they actually are classified like in this branched system. And we are going to start with hydrocarbons, which are essentially just carbon and hydrogen, right? What it sounds like, hydrogen and carbon, hydrocarbons. And that's what most organic molecules are made of. They might have some other things in there as well, but we're starting simple. And we're going to start over here with what are called aliphatic molecules, which really just means that they are not aromatic. Aromatic means it has what's called a benzene ring, has a benzene ring. I'll show you what that is. When you guys see the word aromatic, what does that make you think of?
Aroma.
Right, aromas, things that have smells, right? So essentially, so this is what a benzene molecule looks like. It's a carbon, it's 6 carbons in a circle. See if I can count. 2, 2, 2. And it's got a double bond every other carbon, and then a hydrogen on each carbon. So this is what benzene looks like. And anytime there's a benzene in a molecule, it's probably going to have some distinct aroma. So those are called the aromatics, essentially. Now, everything else is over here on the other side. If it doesn't have one of these benzene rings, it's going to be aliphatic. Okay. Now we have, that is categorized into 2 categories then, and they are either saturated or they are unsaturated. Okay, saturated means that carbon doesn't have any double or triple bonds. So this is no double bonds or triple bonds. And then it is considered saturated, and you'll see why in just a second. And it's considered unsaturated if it has a double bond or a triple bond. Okay. So that's the distinction between those. Now, the reason being these are called saturated, and we'll put this on the next sheet, is because every carbon has 4 single bonds instead of like a double or a triple bond on there. They're called saturated. So we are going to start with alkanes. That's the first thing today is alkanes. These are their formulas. Like a typical formula is a carbon, so many carbons, and whatever number it may be. And then the number of hydrogens it has are 2n plus 2. So it's going to have twice as many hydrogens as carbons plus 2. And then, so this is what it looks like if it is a straight chain. So this is when your carbons are in a straight chain. Excuse me. Okay, now they can also be organized in a ring or a cyclic structure, and those are called cycloalkanes. Excuse me, I'm dying here. These are when your carbons are in a circle, carbons in a circle. Okay. Now, kind of like benzene, except over here, remember, we're under saturated, so there's no double bonds. Okay, so that's why this is not considered a cycloalkane. So cycloalkanes are just when the carbons are in a circle, and it could be however many carbons. Like this is a cycloalkane I'm going to draw down here. When all the carbons are bonded to each other, and then they have hydrogens on the outside. This would be a cycloalkane. It's actually cyclobutane. Okay. And then when you start adding in double or triple bonds, you need less hydrogens. An alkene is something that has a double bond. And an alkyne is something that has a triple bond. Okay. These are words we're going to be using quite a bit. So it goes alkanes, alkenes, alkynes. All right, questions so far? Good. It's a lot of new words. So
What was the
aliphatic, it's
Yeah.
just if it's not aromatic, it's
Okay.
considered aliphatic. Not really a definition you need to know. So okay, so we're starting simple. We're just doing alkanes today. No double bonds, no triple bonds. All right. An alkane, we already said, is called a saturated hydrocarbon. Where'd my pen go? There we go. Saturated hydrocarbon. Okay, that means we have all single bonds. Okay, so all carbon are single, which are also considered sigma bonds. If you think back to 161, you got sigma and pi bonds. A sigma bond is just a single bond. Okay, we were talking about hybridization earlier. That's where that comes from. So all of the carbons are single bonds, and hydrogen can't make a double bond ever. So those are also all single bonds. So this is an example of an alkane. This is ethane, and its formula is CH3, and that's what the molecule would look like in 3D. And this is what it would look like if we draw it in 3D. So it's all single bonds, C to C. And then these are tetrahedral because carbon has 1, 2, 3, 4 bonds. So all of the carbons in an alkane are going to be tetrahedral. They're going to have 109.5 degree angles. Okay. And that's essentially what they're going to look like. So that's a pretty simple one. So on the other page, we said that they have a specific formula. A formula for an alkane, right, was CnH2n plus 2. So if I know that there are 2 carbons, I'm making a formula that has 2 carbons, then it's going to have 2n plus 2 hydrogens. So 2 times 2 plus 2 is 6. So if it has 2 carbons, it has 6 hydrogens. So this is C2H6. That's what ethane is. Okay, so there's a bunch of different ways we can draw these. And that is what I'm going to talk about today. And this actually might make a little bit more sense with some pictures that you might have seen before. So we are used to complete structural drawings. These are like Lewis structures. This is what we usually draw, a complete structural drawing. So what I'm going to use for all of these examples here, I'm going to use propane for our example. I'm going to write that over here. So the example I'm going to use is propane, which is an alkane, and it is C3. And if I have 3 carbons, how many hydrogens would it have? 8, exactly. So it is C3H8. This is an alkane because 2n plus 2. So the structural drawing for this, remember all the carbons are singly bonded. So it goes 1, 2, 3 carbons. And then the hydrogens fill in around the outside. So all carbons have to have 4 bonds. So I would draw 4 bonds on each carbon. And each one of those is to a hydrogen. So this is why it's called saturated. It has like as many hydrogens as possible. Okay, this is propane. And this is the complete structural drawing. So a complete structural drawing shows every single bond, shows every single bond. Like I said, like a Lewis structure, we draw out all the bonds. A lot of the times we like to condense them so that you don't have to draw out the whole thing. And we actually use condensed structural drawings a lot more. So this actually collapses. This is when you collapse the hydrogens that are bonded 2 carbons. Okay, so instead of drawing out all the hydrogens on the outside, I would just say, this is CH3 bonded to CH2 bonded to CH3. So you would draw it like this, CH3 bonded to CH2 bonded to CH3. So that is a condensed structural drawing. Okay, we still show the bonds between the carbons most of the time. Sometimes you'll see it without, but you don't have to show where all of the hydrogens are essentially. Okay, now we can condense it a little bit more and take out all of the bonds. And that's called the condensed formula, because this is what we usually use in like for writing a balanced chemical reaction. So use in a chemical reaction, no bonds are drawn. Okay. So we're not just writing like C3H8. And there's a reason for that, is because that's not what the molecule looks like. It's not like it's 3 carbons in a circle or in a certain way. We know this molecule actually looks like this, CH3, CH2, CH3, which is why it's better to do this for a balanced chemical reaction, because then you can actually see like where the bonds are breaking and what's going on. So you'll see condensed formulas a lot of the time. All right, so you kind of take out all the bonds, and then you got your condensed formula. Now, a new one for you is going to be line diagrams or skeletal diagrams, and it is just the bonds, no letters. Okay, so you write like essentially you're going to draw the lines for the bonds, and each line represents a carbon bonded to a carbon. So I'll show you how to do this in just a sec. So each line represents a carbon-carbon bond, and you do them in a zigzag so you can see where they begin and end. Zigzag them, and then the hydrogens are just assumed, because we assume that it has enough hydrogens on it to make all 4 bonds on a carbon. So if I have 3 carbons, a line diagram for that is this. So each line represents a carbon-carbon bond. So I would be like, okay, this is a carbon, this is a carbon, this is a carbon. And we assume there's enough hydrogens on there to actually make it. So there's 4 bonds. So that is the skeletal drawing. So if you see a bunch of lines, essentially each vertices, I don't know, whatever you want to call it, is a carbon. Each end of the line is a carbon. So this is 3 carbons bonded together. And then you just keep going in a zigzag as you make it bigger and bigger and bigger. Okay. So you'll see a lot of those as well. So these 2, C and D, the condensed formula and the line diagrams, are where you're going to see a lot of the time. Okay. Now, in reality, of course, structures are 3D. We know the angles are 109.5. Okay, so you aren't going to be drawing these as much, but I do want you to like think about the fact that they are 3D structures, and that would be like the VSEPR diagrams. Molecules aren't planar unless that's their shape, but molecules in general aren't planar. They're not 2D. It's not flat. Doesn't actually look like this in a flat plane, right? They stick in and out. All right. Because if you remember anything about sigma bonds, yes, I know my sigma looks like a 6. Sigma bonds can rotate. And rotate. So that means if I have this propane molecule, which is what's drawn over here, all of these can rotate. They're free to move. And so it's still a 109.5 degree angle between all of them. But it is 3-dimensional. So you have some sticking out of the paper, some going into the paper. It's kind of hard to draw them all in 3 dimensions. So just remember that those can kind of rotate. Okay, so how to name these molecules. So you do have to know the base names of the first 10 alkanes. These are like straight chain alkanes, nothing sticking off of them. You are probably familiar with most of these. Methane, ethane, propane, and butane are probably all things you have heard of and may not have known what they were. And then after butane, you'll notice that the prefixes line up with how many carbons there are. Pentane, hexane, heptane, that's 5, 6, 7, 8, 9, 10. Okay, so I do have a mnemonic to remember carbons 1, 2, 3, and 4. It is Mary eats peanut butter. Yes. I don't know why, but that's the one that I learned, and that's the one that I always remember. So 1 carbon is methane, 2 is ethane, 3 is propane, and 4 is butane. After that, it's the normal prefixes. So that's how I kind of remember them. What else did I want to say about these? These, like I said, you've probably heard of these most of the time. Methane, what's methane used for? Gas, yes. If you have anything that runs off gas, we use methane. Methane is what's in the labs, in the Bunsen burners, and all of that. Propane, right? Propane tanks. So you use that's where you hook up to a grill. Butane, yep. Lighters are full of butane. So these are all things that are obviously very flammable. We use them to get energy. Like I said, organic molecules for the most part are really, really good at burning. Okay. Now, what do you notice about the boiling points here of these molecules? Exactly. They go up as they get larger. Okay, so larger chains equal a higher boiling point. Why is that? They're bigger, they have more bonds, they can make more, what's that? Yes, London dispersion forces, okay? They have more LDS, more intermolecular forces, so they stick together a little bit more. So like these are like liquid, heptane, octane. I know you've heard of octane before. That's liquid, whereas methane is always gas. They don't stick together as well. So bigger molecules, higher boiling point. All right. We're getting there. We're doing great. Okay. So the next thing I want to talk about are structural isomers. So we can stick these carbons and hydrogens together a bunch of ways. We've been talking about straight chains if they're all in a line. That is not always the case. We can start branching them off of each other. So you might not be able to read the teeny tiny writing here, but if I have 4 carbons, I can either put them all in a straight chain, and that's called butane, or I can stick one off the middle. This is actually a different structure, and it's called isobutane or 2-methylpropane. And it changes the structure. These are actually different molecules. Those are called structural isomers. Okay, so an isomer is essentially the same formula, different connectivity. Different connectivity. All right, so you just stick them together differently. So 4 carbons actually has 2 isomers. They can look like this, or it can be 3 with 1 sticking off the middle. You can also, so if I go to 5, I have more isomers, 5 carbons. I can either put them all in a row, or I can stick one off of this carbon here, or I can do 3 and then stick one up and one down on that carbon there. Now, these are the only isomers for if you have 5 carbons. Putting a carbon on this carbon, like the second one versus the third one, is the same molecule, it's just flipped, right? So remember that they can rotate. So if I'm looking for a specifically different isomer, you have to actually connect them differently. So if I were to write this one out, it would look like this: CH3, CH2, 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 CH3. But if I write out the condensed form of this one, it's CH3, CH with a CH3 sticking up top, CH2, CH3. And if I write out this one, it's a carbon in the middle with CH3 sticking off all of the sides. So if you do the condensed formula, those will all actually be different. Okay. So if I ask you to make an isomer, you need to connect it differently. Now, when we start branching them, and you probably can't see this, but this one's boiling point here is 36 degrees Celsius. This one is 28 degrees Celsius, and this one is 9 degrees Celsius. So what does the branching do? Yeah, branching essentially lowers the boiling points. Okay, they don't stick together as much when they're all branched off. They can't fit together very well, is essentially what's going on. Okay, so how do we get all of these fun names, right? This is called 2-methylbutane. This is called 2,2-dimethylpropane. That's what we're going to talk about now. And this is a system of naming called IUPAC. There is a conference where a bunch of chemists get together and decide on all of these rules. So if you hate them, I'm sorry, but this is what they decided. And so this is how we name organic molecules. So this only applies to organic molecules, but you will see organic molecules in biochemistry, and a whole bunch of other different branches as well. So these are a different set of naming rules than what you guys are used to for just regular ionic and covalence. Okay, so there are 3 parts to each name. The prefix has to do with what are called the substituents. So those are the things that are sticking off the main chain. All right, so substituents are any group that is attached to the longest chain of carbons. Okay, anything that is sticking off the longest chain of carbons. Okay, we're going to start with just carbon and hydrogen substituents. So over here, these are called alkyl groups. These are substituents. Okay, so these are just carbon hydrogen substituents, and they are called, like I said, alkyl. There you go, substituents. Or groups. A lot of the time we'll just start calling them groups. So if you noticed before, a molecule that is just 1 carbon with its 4 hydrogens is called methane. A group of 1 carbon that would be stuck onto a molecule is called a methyl. So the prefix meth essentially means 1 carbon. Okay, ethyl means 2. So if you have something sticking off of your molecule that is 2 carbons, it's an ethyl group. 3 sticking off is a propyl group, like propane, 3 carbons. Now they can either be attached on the end, or if it is attached in the middle, it's called an isopropyl group. That is attached in the middle. Attached in the middle. Okay, so we're going to look at a couple molecules that have these, and we are going to name them. So the first part of your molecule should be your substituent. So like what's stuck on it. And then the base is the longest chain of carbons, however many your longest chain is. So it could be like hexane, heptane, octane, all of those, okay? And then the suffix tells the family of organic chemistry that we're in. An example of a family is alkanes. Okay, so we are just doing alkanes today. So all of the alkanes end in ane, A-N-E. All of the alkenes, when we get there, will end in ene, E-N-E, and so on and so forth. So we're just starting with alkanes. So we'll say this is what's stuck on it. This is the longest chain, and it ends in A-N-E because there's no double or triple bonds. Okay. So when you look at a molecule and I say name it, you are going to first find the longest consecutive chain of carbons. Find the longest consecutive chain of carbons. Now, remember, these molecules can rotate, so they can bend. It doesn't have to be straight, okay? Keep in mind, they can bend. You're just looking for the longest carbon to carbon to carbon to carbon to carbon bonds, okay? That's gonna tell you your base. All right, the second thing you wanna do is number those carbons, like carbon 1, carbon 2, carbon 3, so on and so forth. So number the carbons. Now from which end? So from the end, I just put the end into one word. From the end, nearest the first substituent. Keep leaving out letters. Nearest the first substituent or group. So you're going to pick your side based on like where things are attached. So number the carbons from the end nearest the first substituent. Essentially, we want low numbers. We want low numbers, if at all possible. Okay, so if I have like methyl group stuck on there, I want to start numbering closest to the methyl groups. Okay, so when we order these in our name, right, the substituents come first. So you're going to actually list those out first and which carbons they are on. So you list the substituents, list the substituents or groups as a prefix with the carbon number they're attached to. So if you have a methyl group that is stuck on carbon 2, we're going to say 2-methyl, whatever, and keep going and going. Okay, so there's a couple notes about these. If there's more than one of a kind of substituent, so if more than one substituent, you have to list all the numbers of where they are. So if you have one on 2 and one on 3, you have to list both numbers. So if greater than one substituent, list multiple numbers. And then you'll use di if there's 2, tri if there's 3, tetra if there's 4, so on and so forth. And so if there's 2 methyls on different carbons, I would say 2,3-dimethyl would mean 2 methyls. The other thing is if there's more than one kind, you list them in alphabetical order. So if I have a methyl and an ethyl, I would list the ethyl first and then the methyl. Okay, so list substituents in alphabetical order. That's the last thing I'm writing on here. List substituents in alphabetical order. Those are all the rules that we need to play by for now. So we're going to do a couple of these, and then we're going to talk about cyclose, and that's going to be about it for today. And then we're going to talk about the paper. Okay, so I'm going to name a couple of these with you, and then I'm going to have you try at least one, if not 2 of them. All right, so I'm going to follow through my rules. Okay, this first one. So you want to find your longest chain of carbons. How many carbons are in the longest chain here? 6. Okay, so my base should be hexane. Okay. Now I do have to write my substituents first. So if my 6 are these carbons here, right? That's the longest consecutive chain of carbons. I have a substituent here and I have a substituent here. Okay. And what are CH3s called? Methyls, right? So if you're not sure what you get used to it, look back here. They're methyl, ethyl, propyl, and isopropyl, or butyl, and there's butyl in that too. Okay, so should I start numbering from the right side of the chain or the left side? Right, because I want my numbers to be small, so you want to number it closest to the substituent. So I would go, that's carbon 1, that's 2, that's 3, that's 4, that's 5, and that's 6. Okay, so I have 2 methyl groups. One is on number 2 and one is on number 3. So this is how you list it. You would go 2, maybe 2, 3. Now you're gonna put dashes between these. Okay, 2, 3, and there's 2 methyls, so I would call it dimethyl. So 2, 3, dimethyl hexane. That is the name of that molecule. Okay, now I'm going to do the one under it. Okay, this one has a couple of different branches. What is the longest chain of carbons in this molecule? It is 8, exactly. Remember, it can bend. You don't have to just use the ones that are all next to each other. I would count them 8, and I'm going to start over here because of the substituents. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so remember, it can bend because there's free rotation around all these alkanes. Okay, all of those single bonds. So I started over here because I have substituents here. Okay, so I'm going to circle my substituents. Got one here, got one here, and then I've got one here. Essentially, anything that is not part of your long chain is a substituent. So this is a trimethyl because I have 3 methyls. And what carbons are my methyls on? Right, 3, 3, and 6. So when you name it, you actually have to say 3 twice, so I know where they are. 3, 3, 6, trimethyl, and then what? Exactly. Octane because of the 8 carbon. Okay, I want you guys to try these two. You can do it. I have faith. Remember, your groups go in alphabetical order. Try to find your longest chain. Okay, so I've got both my answers up here. This one I listed ethyl then methyl because of the alphabetical order thing. This one I listed isopropyl and then dimethyl. The prefix part does not count in the alphabetical part. So that's another rule. But when I numbered this one, so if you can't figure out how I got the octane, I actually started at this carbon. 2, 3, 4, 5, 6, 7, 8. So then my 5 had this group was called an isopropyl because it's attached in the middle. This one has a methyl and this one has a methyl. Questions? Not too bad yet. That's fair. It's fair. There's a lot of really like small rules. It gets more complicated, don't you worry. Okay, so now we're gonna do circles, cycloalkanes, and it's like just the same thing except you say cyclo. Okay, so like if it's 4 things bonded in a circle, which is really a square, it would be called cyclobutane. That's it. So a cycloalkane, to make a cycloalkane, essentially you take off a hydrogen from each end of a chain and then you stick them together. So it actually has 2 less hydrogens than what a regular alkane does. So cycloalkanes remove 2 hydrogens, H's, from an alkane. You can only do this with 3 or more. 2 obviously can't make a circle. So from an alkane and connect the carbons to form a ring. And connect C's to form a ring. So the smallest one you could possibly make is cyclopropane, where I have C, 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 and then each of them are to have hydrogens on the outside. Their skeletal structures or their bond line structures actually look like the geometric shape. So this one's a triangle, this one's a hexagon. That's what I was gonna say. That one's a hexagon. And so on and so forth. They just literally make the shapes. Now you can stick stuff off of those too. So we'll have substituents on these as well. But this is just called cyclohexane and that one's called cyclopropane. Okay. So that's like what your structures are going to look like. Now, again, these are 3-dimensional. Now, when you start getting chains and you're trying to like form them into circles in 3D, you get all kinds of different stuff sticking out. So for example, and cyclohexane is used a lot for this. It's used for a lot of molecules. Cyclohexane, remember, these are not planar. Okay, so rings are also not planar. Rings are also not planar. So when they try to get as far away from each other in 3D space, right, electrons are trying to repel each other, you start to get these weird shapes. So cyclohexane can either look like this, and we actually call this the boat conformation, or it can look like this, and we call this the chair conformation, because supposedly it looks like a chair. Now, you don't have to memorize and be able to draw these, but just the fact that they are three-dimensional and stuff is sticking out is really important. Okay, so if we're naming cyclo things, all right, so this is our naming cyclo things, you still start with the substituents. Okay, so if you're naming these, so if naming cyclos, you might be like, well, it's a circle. Where do I start numbering my carbons? You just start at the first substituent. Okay, so if you're naming cyclos, start your numbers at the first. I'm just going to abbreviate it sub. I think you guys get it. Okay, first substituent. So you just pick where number 1 is and you go from there. And you can go clockwise or counterclockwise, whatever makes your numbers as small as possible. That's it. Now, besides cyclos, the only other thing I'm going to throw in at this point is haloalkanes. What does halo sound like it comes from? Yes, halogens. Halogens. So if we substitute one of our hydrogens with a halogen, where do you find the halogens on the periodic table? Yeah, group 7A, that's where those are. So fluorine, chlorine, bromine, iodine, acetine's not going to stick on anything. You are going to name these as a group, like as a substituent as well. So haloalkane is replacing a hydrogen with a halogen. And you got to tell me where those are too. Okay, so the prefixes are iodo for iodine, chloro for chlorine, bromo for bromine, and fluorine's not on here. I'll list it over here. Fluoro for fluorine. Those are the only ones that you will see. And again, you have to tell me where it is. Okay, so for example, this one is called 1-bromo 2-methyl propane, because this is carbon 1, 2, 3. There's a bromo on 1 and a methyl on 2. Still in alphabetical order. That's why they list the bromo first and then the methyl. And that's it. So that's like the most complicated that we are going to get for now. So name each of these alkanes. Notice these are cyclos. So where would I start numbering on this one? Yeah, I would start with this one. You could start with the other one. Doesn't really matter. Just make your numbers as small as possible. So I would go 1, 2, and so on and so forth. So this would be 1, 2, dimethyl, what? Yep, cyclohexane. Yep. Because there's 6 carbons. Dimethyl cyclohexane. And yes, that last part is all one word. Okay, don't put spaces in there. Yes, everything is going to tell you it's spelled wrong. It's not. All right, so you guys name this one. Okay, what is it? Yeah, cyclobutane, because it's 4 carbons and bute is the prefix for 4. Okay, this next page is all examples. So I'm going to let you guys kind of work through these at your own pace. Okay, and I'll put up the answers. So if you want to ask questions, you can. And like I said, that is all we're doing today. So I'm going to give you, I don't know, 7 to 10 minutes to work on these. And then I'm going to chat about the paper before the librarian gets here. Okay. So this one is line diagrams, and then one about isomers. Oh, I guess I should write the boiling point part here first. Okay. We've talked about boiling points. So go down here really quick, guys. We already talked about, this is the most important one, larger ones, of course, have higher boiling points. Okay, however, if they are branched, they're a little bit lower. So the more branched it is going to be a lower boiling point. And then cyclos are actually a little bit higher. Cyclo makes it a somewhat higher boiling point. Just because of the way that they can like kind of pack together and stuff. So, all right. So like I said, I want you guys to try this page. I'll put the answers up. I'll try to zoom out so you can see it as you're working. And that should be good.